In this video lesson, we're going to talk about vectors, vector diagrams, and how we can draw vector diagrams in different situations. So before we do that, we need to first know what is a vector. A vector is defined as a quantity that has both a magnitude and a direction. And we've seen this already in Unit 2 and Unit 3, but in Unit 4 it's going to become very important. So a vector, once again, is something that has magnitude and direction. Now how do we show that in a diagram form? A vector diagram is going to be an arrow that depicts a vector. Notice that a vector is going to be drawn to scale and it's going to have a direction. So let's take, for example, this blue arrow that we see on the screen. This would be an example of a vector diagram. This vector is drawn to the right and it's also drawn with a certain scale. Now, there's a couple things we need to know about vectors and how they're drawn. First of all, there are two parts to a vector. There's the tip, which would be right at the very end where the arrow is. This may also be called the head of the vector. And then there's the tail of the vector, which is at the very end. This will be important later on when we start doing vector addition. Also, some things to know about vectors. The longer the arrow, the longer or bigger the magnitude is. So for example, if I actually made this arrow longer, then that would mean the magnitude is bigger. Finally, when you have vectors that are facing a certain direction, you can flip their directions by changing the sign of it. For example, if this was vector b, then negative b would just be the same length but going the opposite direction. Finally, what are some examples of vectors? Well, we've already seen some in this class. We've seen examples of displacement, velocity, and acceleration. And in Unit 4, we're going to look at a fourth type of vector known as a force. Remember, anything that has magnitude and direction can be drawn as a vector. Alright, so let's go ahead and start looking at some examples here. We have here an example of an adult is pushing a table with 50 newtons and a child is helping push from the same end with 15 newtons. We want to first know, one, how do we draw the total vector, and then two, what would that numerical value be? This is called vector addition. On this screen, we're going to start with some simple vector addition, and that would be linear, meaning it's just one-dimensional. So imagine here you have an adult that's pushing a table. Here's the table, and here's the adult that's pushing the table. Then, a child is also helping push the table from the same exact end. If you look, it makes common sense that both of them, since they're pushing in the same direction, would have a total or additive vector that's adding together to help each other out. We're going to show those with vector diagrams right now. So for the adult, I'm going to use red, and for the child, I'm going to use blue. So for the adult, I want to draw 50 newtons. Now remember, I said vectors are usually drawn to scale. Typically, it would be appropriate just to do a qualitative drawing, but since we have a scale here on the screen, I'm going to use that. 50 newtons would be all the way out here. So that would represent the vector diagram for the force that the adult is pushing with. Now the child is also pushing with in the same direction, but pushing with 15 newtons. So notice my direction needs to face the same way, and I'm going to go ahead and make it now go to 15 newtons. The final thing is I would want to do vector addition. Since they're both going in the same direction, they're going to help each other. Anytime you do vector addition, you want to do tip to tail. So what that means is I'm going to take my first vector, and the tip of it, which is right here where the arrow is going to be lined up with the tail of the other vector. So just like this. So the resultant vector then would be drawn just like this. And so the total vector for that would be 65 newtons. Let's look at a different situation. Now, the same situation, an adult and a child, but notice the adult is pushing a table of 50 newtons and the child is getting in the way, pushing from the other end with 15 newtons. Now, the adult's vector is still going the same direction, but the child's vector, same magnitude, is going to be flipped in the opposite direction, looking just like this. We would still put them tip to tail, and then we would draw our resultant vector. Now, the resultant vector would be this length right here, and then you have to ask yourself, would it be to the left or to the right? Since the red vector pointing to the right is longer than the blue vector pointing to the left, my resultant vector would end up being pointing to the right. The adult is winning in this case. But the resultant or total vector would end up being 35 newtons to the right. These were some examples of linear or one-dimensional vector addition. Let's take a look at some examples where maybe it's not one-dimensional, but it's two-dimensional. So let's take, for example, we've got a couple of vectors here. I've got my red vector, and we'll give it a length of about 6 squares right there. And I want to add to it a blue vector, and we'll say the blue vector goes over 4 squares and down 3 squares, just like that. And I wanted to add those two vectors together. We're still going to use tip to tail, but notice this time it's not going to be linear. It's going to create a shape. So I'm going to take the tip of the red arrow and line it up with the tail of the blue arrow, just like that. The final step is we're going to want to connect those two vectors. And then the question is, which direction will it go? Well, there's two ways to solve for this. The first way to solve for this is qualitatively. Just think about it for a moment. You have some sort of vector that's pushing to the right completely, which is the red, and then some sort of vector that's pushing down and to the left. If you think about it, if you added these two together, it would create a downward vector that looked just like that. Now, there's another way you can do it, and it's quantitatively. Let's think about this. This red vector right here has a horizontal length of 6. Now, there is no vertical since it's completely horizontal. Now, let's look at the blue vector. The blue vector actually is diagonal, so has a little bit of vertical and a little bit of horizontal drawn just like this. We can split that up into its squares. What would be the length of its vertical? If you look, it's 3 squares. What would be the length of its horizontal? If you notice, it would be 4 squares. And so, let's think about it. The total vertical component of my result would be 3. And so, I'm going to draw that out to the side so we don't get confused. There's the 3 right there. Now, let's look at the horizontal. The horizontal actually has 2 parts. We've got 6 units going to the right, but 4 units that are going to the left. What would be the total of that if we were to do vector addition for just the horizontal? The total would be overall 2 going to the right. And so I would show that just like that. Now that we have those two components, the vertical and the horizontal, we can connect that. And it's clearer to see in this demonstration right here that you have a vector that goes a little bit down and a little bit to the right, which would create this vector right here. And if you notice, that vector lines up exactly where we had it right here. Let's do another example so we can see one more application of this. All right, let's take, for example, now 3 vectors. Let's say we have one vector that goes 2 to the right. Let's say we have another vector that goes 4 down. And then let's throw a third vector in there. Let's take this orange vector right here and say maybe it's diagonal. It goes over 5 and down 2. And I'm going to label this. This will be vector A, this will be vector B, and this will be vector C. All right. If we wanted to add those together, we're going to do that tip to tail. So A is going to come over here. I'm going to line up B tip to tail, and then I'm going to line up C right there. Now, the rule with vector addition is you need to add your resultant in, starting where you started and ending where you finished. So in this case, it would be just like this. And notice the direction. It would go down. We know it's going to go down because if we look at our vectors, it makes sense that we've got vectors in blue that are going down and vector in orange that's going down and to the right. Now, it does not matter which order that you add things. We added it in order of A plus B plus C. But we could have added it in order of B plus A plus C, or C plus B plus A. This comes from math. Just like 1 plus 2 plus 3 equals 6, so does 3 plus 1 plus 2. It doesn't matter which order you go in. So let's mix things up. Let's say I started with the blue first, then I added in the orange, and then I ended with the red. Notice my resultant should still be the same, and we can see that it is. So it doesn't matter which order that you add the vectors in, so long as you add them tip to tail. The next section of the video has to do with vector resolution. Vector resolution is all about taking vectors that are not perfectly horizontal or perfectly vertical, but that are diagonal, and splitting them into their equal components. So let's take a look at these two examples here. I'm told that I have a vector that is 450 newtons, and it's 60 degrees south of west. So let's go ahead and draw that in. 60 degrees south of west. Well, what that looks like is it's going to be going west, which is right here, and then just going a little bit south of there. So we're going to have an angle just like this, right here. So let's go ahead and draw that in with my vectors over on the left. Now, I'm going to just go ahead and make my vector of 450 newtons just be this length, because we just want to look at it qualitatively for right now. So there I have it. My vector is 450 newtons, which represents this whole length. And notice that it is 60 degrees south of the west reference. Now, I also need to add in my second vector. My second vector is 200 newtons, 30 degrees north of west. So I'm going to do that in red. So my second vector will be the red one here. Notice it's going to be shorter because 200 is less than 450. Now, what direction does it go? It tells me that it's 30 degrees north of the west axis. So I'm on west right here, and I'm going to go 30 degrees north, which would be about right there. Once again, we're just getting the general idea because we're going to do the math later on. So there's 30 degrees north of west, and right here is 60 degrees south of west. And this is, once again, not drawn to scale, just getting the idea. What we now want to do is we want to go ahead and do vector resolution. Notice that both these vectors are not horizontal or vertical, they're diagonal. So they both have vertical and horizontal components that we need to break apart. Let's go ahead and do the first one, the 450 newtons, the one that's in the southwest quadrant. All right, I'm going to go ahead and break that apart. I notice that it has a little bit of vertical, which would be right here, and it has a little bit of horizontal. So I'm going to go ahead and find out what those sides would be. I know that my hypotenuse is 450 newtons, and that my angle is 60 degrees. So I'm going to figure out what is my y component and what is my x component. All right, to find the y component, we're going to go ahead and use sine. Sine of 60 degrees equals opposite, which is y, over hypotenuse, which is 450 newtons. Now make sure that your calculator is in degrees, not radians. So sine of 60 degrees is equal to approximately 0.866, and then times by 450, and our y value should be approximately 389.7. So I'm going to go ahead and write that over here, 389.7. Now, let's go ahead and do the same thing for x. For x, it's going to be cosine of 60. And cosine of 60 equals x over 450, which is the hypotenuse. Now, cosine of 60 is one of those special angles. It's 0.5 times 450 is going to give us a value for x of 225 newtons. And so I'm going to go ahead and write that up here, 225 newtons. So I just did vector resolution for my first angle. What we're going to do now is we're going to do the exact same thing, but we're going to do it for the red vector, or the 200 newtons. So I'm going to go ahead and draw that in, and I'm going to draw that in with black so we can see it a little bit clearer. So I know that my red vector has a little bit of x component and a little bit of y component. Now, the y component is going to be right here, and the x component is going to be right here. We're going to do the same exact thing. So let's go ahead and do the y component first. The y component is going to be sine again. Sine, but this time it's 30 degrees, equals my opposite angle, or excuse me, my opposite side, which is y, over my hypotenuse, which we know the value of that is 200. So sine of 30, which is one of those special special angles, is 0.5 times 200 gives me a y value of 100 newtons. That's going to be what's over here for the y component. Now let's go ahead and do the same thing for the x component. For x, I'm going to go ahead and do cosine of 30 equals x over hypotenuse, which is 200 newtons. The cosine of 30 is approximately the 0.866 times 200 is going to give me approximately 173.2 newtons. And so I'm going to write that in for the x right here. All right. Now what I've done is I've split my two vectors that are diagonal into their x's and their y's. Finally, let's go ahead and kind of summarize what we've learned here. First of all, let's focus only on the 450 newtons. For the 450 newtons, what did we find out? Well, we found out that it had a vertical going down of 389.7. We also figured out that it has a horizontal going to the left of approximately 225. All right, what did we figure out for the 200? For the 200, we figured out that it has a vertical going up of approximately 100 newtons. And we figured out that it has a horizontal also going to the left of about 173.2. So the final step in vector resolution is to just add those together. It's easier to add vectors when they're perfectly horizontal and vertical. So I'm going to do that in green. All right, let's do the vertical first. Notice that the first vertical is facing down, the second vertical is facing up. So if you were to add those two vectors together, you would end up subtracting them. 389.7 minus 100 gives you a net force in the vertical of 289.7, and the direction would be down, since the down vector was bigger than the up vector. So this would be 289. All right, let's do the same thing for the horizontal. The horizontal would be 225 to the left and 173.2 also to the left. Since they're both in the same direction, we're going to end up adding these two together. 225 plus 173.2 gives you 398.2 in the horizontal component. What we would do there is add that using our tip to tail, just like this. And that would be 398.2 newtons. The final step in vector resolution, now that you've got those two, is to draw your hypotenuse and use Pythagorean theorem to figure out what your resultant vector would be. So we have 289.7 squared plus 398.2 squared, and take the square root of that answer. Your resultant vector would be 492.4 newtons. So we can see that we have our resultant vector between these two vectors right here would be 492.4 newtons. Now what we're going to do is we're going to figure out what would the angle be of this vector. The final step, like I said, is to look at the angle that this vector makes. The way I've drawn it right here, I'm going to go ahead and solve for this angle right here, this theta. So this is where we're going to use inverse functions. Now, since we know all three sides, you can use whatever inverse function that you feel most comfortable with. I'm going to do sine since that's just habit, but you can use inverse sine, inverse cosine, or inverse tangent since, like I said, you know all three sides. So I'm going to do the inverse sine of my opposite over my hypotenuse value. My opposite with this theta is going to be 398.2, and my hypotenuse value is the 492.4. Once again, make sure you're in degrees when you're doing this. But when you do inverse sine of 398.2 divided by 492.4, you should get an angle of approximately 53.97 degrees. Now, what is the reference of that angle? Well, you can kind of imagine this right here is where your north, south, east, and west quadrant is. So what would that angle be referencing? It would be 53.97 degrees west of the south direction, or south axis. If you wanted to do the complementary angle of that, that would equal out the 90 degrees, you could also write, and it would be correct, 36.03 degrees south of west. And if you did that, you would be talking about this angle right here. So the first time you see vector resolution, it looks like it's very difficult, but it's not as hard as it seems. You just need to do practice with it. Let's end this video by doing one problem together using not forces, but we're going to use velocity vectors. So a motorboat traveling down a river at 4 meters per second east encounters a current traveling 3 meters per second north. So the key thing, first of all, is that you have a river, and I'm going to draw this in. Here's your river, and it's traveling east. So this is the east direction. And what's happening is there is a current that is traveling north. So this is east over here, and north would be up here. So there is a river current that's pushing, you're told, in the north direction. All right, the first question says, what is the resultant velocity of the motorboat? All right, so we know that the motorboat has its own velocity of 4 meters per second going in the east direction, but the river is pushing 3 meters per second in the north direction. So the resultant would be a little bit like this, and it would be in the upper region. It'd be going up and to the right. And if you know your special triangles, you can figure out that this would be 5 meters per second. If you don't know your special triangles, you could just do Pythagorean theorem, since this does make a right angle right there. Number 2 says, if the width of the river is 80 meters wide, then how much time does it take the boat to travel shore to shore? So basically what it's saying is if the width of the river right here was 80 meters, and as time was going on, this boat started to shift more and more and more to the other side of the shore because of this 3 meters per second. The question is, how much time does it take for the boat to travel to that shore? So, what are some things that we know? Well, we know the distance is 80 meters. We know that the velocity is 3 meters per second. Notice I'm using 3 because that's actually the velocity that's pushing the boat from one side to the other. So we need to use this velocity since that's what's actually coming into play. And then the time is what we're going to solve for in this case. So if we know that, we're going to go ahead and use a formula. Since there's no acceleration, since it's not speeding up or slowing down in the north direction, we can just use a simple equation of velocity equals delta x over delta t. We know what velocity is and we know what delta x is, so I'm going to rewrite this equation to solve for time. And that would be delta x divided by my velocity. My delta x is 80 meters, and I'm going to divide by 3 meters per second. If I do that, that's going to go ahead and give me my time that it would take to go across the river. And that would be about 26.67 seconds. Finally, number 3 says, what distance downstream does the boat reach the opposite shore? It's assuming in this amount of time. So in 26.67 seconds, when it finally does reach the opposite shore, how far down the stream does it go? Well, the downstream velocity is the 4 meters per second right here. So in 26.67 seconds, and if it's going a velocity of 4 meters per second downstream, how far would it go in that amount of time? So we're going to use the same equation that we did over here. We're just solving for a different variable. We're going to go ahead and solve for delta x. So I would rearrange the equation to be delta x is equal to velocity times delta t, or time. My velocity is 4 meters per second, and my time is 26.67 seconds. Multiply those out, and I would end up getting my delta x downstream is approximately 106.67 meters. This ends the video on vectors and vector addition with vector resolution.